Hello, today we'll be seeing floating point numbers. Let's create a float. Put it in the label. And now we can show real numbers as well. We can also ignore the first zero. This is the same as 0.01. We can also use integers as float by adding a dot at the end. This is basically 1, but it's treated as a float instead of an int. That's necessary when we want float division. For example, 3 divided by 2 is 1.5. However, if both are ints, the result will also be an integer. So the decimal part goes away. If we turn 3 to a float, the result is float, so we get the actual value. It depends on whether we need the quotient of the Euclidean division or the actual division. Floating Godot is 64-bit double precision floating point number, just like double in C++. It has 14 reliable digits, and this is approximately the largest float. Actually, there's no point to use a label, it won't even fit. We'll use the print function to show the number down here. This is the greatest float. The e means multiply by 10 raised to the 308. This is the same using math operators. And we get almost the same number. It has an error here. If we go back, we see one of the ones is gone. That is just due to float precision issues. By the way, I use floats because the integers would give a much different result. Let's remove the dots. That is because their maximum value is much smaller than 10 to the 308 and it wraps around. Now, let's try to increase the number. No change. Let's multiply it by 2. And we get infinity. F1 brings up the documentation pop-up. Search for inf, positive infinity. This is the result of float division by 0. For negative, use the minus. Okay? We'll see more about this in a separate video. Okay, we saw the max, let's see the minimum float. It's pretty much the same, but with a minus at the front. And if we multiply by 2, we now get a negative infinity. Many methods and properties use the 32-bit single precision. This is equivalent to float in C++. This has only 6 reliable decimal digits. For example, classes like vectors use 32-bit floats. This can change if we compile Godot with precision equals double. Math done using the float type is not guaranteed to be exact and will often result in small errors. Okay, first let's try vector 2. We'll use the max floats. And now we get infinity. That's because float is 64 bits, but the vector is 32. Let's try a smaller number. Okay, this works. Now let's see the amount of decimal digits. It says 14. Okay, that's 14 digits. 9 plus 5. It prints accurately. If we add another one, it prints something else. Now it ends with 46 instead of 45. That is because it rounded the number. If we use another number, it rounds it again. Rounding basically increases the next digit by 1 if the leftmost digit we're removing is 5, 6, 7, 8 or 9. That means that 5 will change to 6. If we have 0, 1, 2, 3 or 4, we just remove the left part. 5 remains the same. One last thing. Let's get 8 ninths. Without a dot. It returns the quotient of Euclidean division. Now turn 1 into float. And we get 0.13h and a 9 at the end. Normally the result would be 0.infinite-h, but there is a limit on how many digits we can have. Let me print the value so I can copy it. Now if I multiply this by 9, it gives 8. It's like we remove the denominator. Let's copy this value and place it here. Technically that should also be 8, but we get something close to 8 instead. It has 1 as the last decimal digit. If we tried using equals equals to check for equality between floats, it wouldn't work. What? Alright, we don't need this str anymore. False because the number was not actually 8. Instead, we were comparing 8 with the next float we could use. Despite the small difference, the numbers are not equal. That is where is equal approx comes in. Returns true if A and B are approximately equal. A and B are within a small interval epsilon of each other. Epsilon depends on the magnitude of the numbers. Infinity values return true if they have the same sign. A is equal approx. Now we pass the two values. And we get true. Despite the numbers not being truly equal. Now let's see 0 approx as well. It's pretty similar to before, but now we only need one number which we compare to 0. Now let's subtract the number from 8. Same here. We get true, despite the number being this. Here's the description. This one is faster than is equal approx with one value being 0. The documentation suggests using these methods when it comes to comparisons, instead of equals equals. Okay, that was it for the float numbers. In the next video we'll see constructors. Till next time.